Participants, do you have any questions? So shall we proceed on to the next session? Sir, thank you so much, sir. It was really a very wonderful session, and you have explained the concepts as well, the theoretical part as well as the demonstration was too good. Thank you so much for the session and the time, sir. Really,
Thank
we are, just thank you so much for giving your time as well. The presentation and the content was too good. It was useful as well.
thank you.
Thank you, sir. Sir, and one more information, we have validatory after the session by 6:30. Please join, sir. The same link only.
Sure, ma'am. Sure.
Okay, sir. Thank you so much, sir. Thank you. Participants, we shall now move on to the next session. Already our resource person has joined. Sir Zaidan, sir, can you hear me?
Yes.
Yeah, I made you as a presenter. Oh, yes, sir.
Can I share?
Yeah, 1 minute. Yeah, our resource person is here. I now request Dr. Shweta to give introduction.
Good evening. Welcoming you all for session 13, Quantum Technologies for Beyond 5G and 6G Networks by Dr. Engin Zaidan. Dr. Engin Zaidan is a senior researcher in the Services as Networks at Centre Tecnològic de Telecomunicacions de Catalunya in Barcelona, Spain. He received his PhD degree from the Department of Electrical and Computer Engineering at Stevens Institute of Technology, Hoboken, USA, MS and BS degrees from the Department of Electrical and Electronics Engineering at Middle East Technical University, Ankara, Turkey. He worked as an R&D engineer for Avia. He also has worked as a senior R&D engineer at Turk Telecommunication AS and a part-time instruction at Electrical and Electronics Engineering Department of Oisen University. Dr. Zaidan has been primarily responsible for carrying out European Commission and nationally funded research activities at CTPC. He is currently the project coordinator of the Horizon Europe Unity 6G European project. He has also been involved in other European level projects such as H 2020 projects, 5G growth, and Clear 5G. He is a co-author of over 150 plus papers in international journals and conferences and 12 patents, 11 granted in Turkish Patent Institute and 1 granted under European Patent Office. He has given 15 plus tutorials on data engineering for networking, as well as on quantum secure 6G at various conferences. His research interests are in the areas of telecommunications, data engineering, science, and network security. So welcome you, sir. And you can take over the session, sir.
Thanks a lot for the introduction, Dr. Shweta. So I can share my screen if you want.
Sir, you can share.
Okay, so I hope you can see my screen.
Yes, sir, it is visible.
Okay, thanks a lot for inviting for this talk. So I will actually talk about quantum technologies in the aspect of the 6G networks. So we will try to give a basic description of quantum applications in terms of telecommunication networks. So this is the outline that I am planning to do. So first, I will give an introduction about network security in 6G, about this architecture and how it is evolving when we move from beyond 5G to 6G networks. And then the most of the presentation, I will focus on one aspect of the quantum computing, which is more or less on the quantum key networking domain, quantum key distribution. So I will try to give an overview of how we can integrate what is the definition of quantum key distribution, how we can integrate this technology to 6G, and then in the last 20 minutes or so, I will try to show you a simple demo so that the participants can get more hands-on experience on how QKD is working. And then, please feel free if you have any questions. Please feel free to interrupt. I would be happy to answer questions while the presentation is ongoing. So I think this has been given in the introduction, so I will just skip this. So I am at CTTC and my research areas on network security and communications aspect. So first, let me go to the introduction of network security for 6G networks. So as you may know, the 6G is evolving from previous generation of 5G. And this picture is showing how the evolution has evolved. So over decades, we have moved from 2G, 3G, 4G. And now the estimate is that when we after deployment of 5G, the next deployment of 6G is expected to be around 2030. So what is new in 6G compared to 5G? So in the ITU or IMT 2030 vision, in addition to this classical massive communication, immersive communication, and hyper-reliable low latency communication, there are new dimensions that has been added by ITU, International Telecommunication Union, which is this AI integration, ubiquitous connectivity, and this sensing and communication. So these are actually some of the new dimensions that has been added to 6G. So this has also given some enhanced capabilities. So in addition to what we already have in 5G in terms of these KPIs, reliability, latency, we also have actually new capabilities which are related to this AI, coverage, sensing, sustainability. So these are actually some of the new KPIs that comes with 6G. So when we look at the timeline, so the roadmap is defined by 3GPP. 3GPP is the standardization body that is trying to standardize 6G network. So we see this. The plan is to have a commercial launch at the end of 2029. But to come to that point, we need to have define the requirements, which are already done in March 2025, 6G requirements, and some key architecture decisions needs to be taken, which will be done in December 2026. So there is a release evolution for 6G, and it is on the roadmap that we will have this, let's say, commercialization in the coming years. So it's not only the 3GPP that is defining the standards. Of course, we also need innovation and regulation bodies. ITU is defining these requirements for 6G. So this is actually the roadmap for ITU. They already have this IMT 2030 roadmap. In addition to that, there are also innovation bodies like this European Union or NextGA in United States and in other parts of the world that are trying to bring some new innovations that would help standardization bodies to put them into the standards. For example, O-RAN ALIs is one aspect. that is trying to standardize the radio access network. So what kind of technological trends we have in 6G? So there is, as you can see here, comparison to 5G, we have new technologies. Of course, 5G has this software-defined network function virtualization. But now with 6G, we have blockchain, some native AI functionalities, maybe things that are related to quantum computing could also be part of the 6G network. This is what we are thinking about. But when we look at the applications, we see different applications, more diverse applications, holographic presence, UAV-based mobility, digital twin, smart grid 2.0, connected autonomous vehicles, Industry 5.0. So these are all new kind of applications. And on top of it, we also have new requirements which are related to scalability, privacy, and security. Of course, this is also AI and how to make this AI native systems to be in line with ethical constraints, regulatory constraints, and there are many things that needs to be handled to make these applications effective in 6G networks. So there is this kind of what discussion about what will be the architecture of 6G in comparison to 5G. So I think I put this picture just to show you that this is a little bit different than the 5G evolution, because in addition to regular control plane, user plane, data plane functionalities in the architecture, as you can see, we also have native AI functionalities in each functional block, and also the security functionalities also embedded into each functional block. So this is showing the trend that we need to have for each functions that we put. We need to have this native AI support and native security by design support. For example, as you can see in each of the boxes, they can either be control plane, user plane, but in each of these boxes, even the newly added boxes like sensing functions, they have these AI and security functionalities embedded into the architecture. So when we look at the security domain, we also see this trend changing because when we move from, let's say, previous generations, 3G, 4G, to 5G and 6G, in addition to the changes in the applications, we see this web applications, mobile applications, IoT, and then autonomous systems, multi-sensory extended realities. We also see the trend in terms of security is also changing. For example, in 3G, we were talking about IP traffic vulnerabilities. In 4G, we went to trends coming from the new services and applications. And then in 5G, we have this cloud network function virtualization and SDN, which brought some new vulnerabilities. And now with 6G, we will have these AI-powered systems that will come from different layers. For example, from this domain, we can see some examples like AI/ML-based intelligent attacks and zero-day attacks that when you put these new applications. And also, if there is some enhancement in the physical layer, of course, there will be new attacks in the physical layer. And then another type is this, of course, the quantum attacks with the enhancements of the quantum computing, new dimensions or attacks dimensions will emerge that could emerge in 6G. So this is actually showing the picture for 5G networks. In the 5G networks, we had these IoT devices, access network, mobile edge clouds, backhaul network, some operator cloud environments, and then we were connecting to another operator environment. We have this remote services systems connecting to the backhaul network. So this was more or less summarizing the kind of attacks we were trying to cope with related to, let's say, denial of service attacks in the cloud, or some kind of slice resource theft in the backhaul network, or things related to, I would say, fake base stations in the access networks, or some privacy breaches when you are trying to utilize the massive devices. So these are all kinds of threat landscape that were, let's say, discussed during the 5G deployment phases, and still people are trying to protect the network against this kind of attacks in the 5G domain. But when we look at the 6G, it is a little bit now getting different. Now we have more multi-stakeholders. Supply chain is coming because now we have multiple vendor software, and they are mixed of open software and vendor-specific devices. And then now we have more heterogeneous clouds, heterogeneous networks, because now we have this, I would say, terrestrial networks, non-terrestrial networks, public networks, private networks. So it's becoming more disaggregated, and now we need to have this, and also becoming more distributed. And then these are bringing some new challenges. And now the trend also is to have an open interface. In addition to this, let's say, closed system, you want to open the interfaces to outside world, and then there will be interoperability cases that needs to be, let's say, softened. Disaggregation of the functionalities is something that is coming, of course, with Open RAN. I will give an example in the next slide. And of course, there is millions of subnetworks. It's not only one network, but a bunch of networks that are connected to each other. So you need to manage this complexity. And of course, the devices are going to be increased with billions of devices. So this is actually summarizing the security threat landscape for 6G, actually showing some kind of threats in the orchestration when you want to manage the resources or let's say services. You would have this kind of say open API attacks, AIML attacks, closed loop network automation attacks. In the platform domain, again, you can have attacks on the privacy or threats on the edge, on the cloud, or when you are going to specific functionalities, again, you can have physical layer attacks, and also at the end user devices. These are also privacy and DDoS attacks on the devices. So these are actually some of the envisioned things. So since there is innovation, in parallel, the attack surface is also increasing with the 6G. This picture is also showing security and privacy issues with enhancements in the technologies. For example, here, when you have distributed AI, you will need to have this quantum communications, blockchain-based systems. These are all also bringing some security and privacy issues. For example, with quantum communication, you could have this encryption communication issues, and with the blockchain, maybe some blockchain-related authentication, access control systems. So these are actually all things that, let's say, with the enhancements of the technologies, you can try to solve these security issues with some technologies that is already coming up. So yeah, so just wanted to say here in this picture that there are applications and there are solutions that are bringing these applications, but there is also these security privacy issues that needs to be solved when we want to try to put these applications into the system. So this is actually summarizing the threat landscape taxonomy. So more or less, I think it's inheriting things from the 5G and also adding more into the picture. I will not go to details of this taxonomy, but I will just focus on one aspect, which is maybe in the next slide I will show. Before that, I want to also show the this Open RAN Open Radio Access Systems, which you have this native AI support with intelligence controllers. You have this non-real-time radio controller, near real-time RAN controller, which all have their own AI applications, which is called RAP, XApp. And you also have this Open RAN system underneath, which has this control, centralized unit, distributed unit, radio units. And they are all connected to this Open RAN front hall, these interfaces, which are well defined between the service management orchestration and the rig and the devices. So just wanted to emphasize that in addition to these general attacks that could happen to the radio, you also have these attacks related to intelligence, because now you are bringing these rigs into the picture. And then you have these data model poisoning attacks, because these are actually envisioned to be open source applications. So you will have attacks on the open source software. And of course, things coming from the 5G related to virtualization, DNF, virtual machine migration, and also things that are related to open interfaces, spoofing attacks or rogue RUs. So this is actually showing one example that if you try to move towards these open interfaces, how easily your attack surface can increase with the additional new technologies. So there are different technology enablers. So these are actually some emerging technologies for 6G. So quantum safe systems, quantum key systems. So quantum cryptography is actually one way to resolve, let's say, some of the threats that is coming from this.
Chirag, hello. Good evening.
Sorry. So quantum attacks is actually we could try to resolve them with. Sorry.
ಗೊತ್ತಿಲ್ಲ ನನಗೂ ಅದ್ರ ಆ ಕಂಪ್ನಿ ಬಗ್ಗೆ ಅಷ್ಟೊಂದು ಐಡಿಯಾ ಇಲ್ಲ. ಇದು ಗ್ರೂಪ್ ಅಲ್ಲಿ ಏನೋ ಶೇರ್ ಮಾಡಿಲ್ವಾ ನಿಮ್ಗೆ ಅದ್ರ?
I guess there is a background noise.
Yes, sir. I just muted them. Please proceed, sir.
Okay. Okay, thanks. So what I was saying, that there is these enablers that are trying to, let's say, mitigate the effects of the attacks. So we will try to focus on quantum key cryptography and especially quantum key distribution in this picture, in this presentation. But of course, there are others like blockchains that are trying to help assist against these kind of attacks. So when we try to go to do quantum computing in 6G, there are different aspects that is coming with quantum computing, like quantum assisted communication, quantum machine learning algorithms, and of course, quantum security. So there is different dimensions to quantum security. One aspect is post-quantum safe cryptography. The other one is making quantum resistant hardware. So you can also do this quantum key distribution. You can exchange the keys with the principles of quantum key distribution. So this is actually let's say, trying to resolve against this kind of quantum-based attacks that could come, and you will try to resort to one of these solutions to help you resolve this. So we try to actually, in this, I'm just showing a high-level overview of how you can put this into the picture for 6G. For example, here we have, let's say, regular core network, radio access network, and the backhaul network. And you can have another. So these are actually enhanced by quantum assisted communication and quantum assisted communication. So the quantum assisted communication and quantum assisted computing processes. For example, in the case where you have this RU, DU, CU connections, you can have this quantum key distribution or quantum communication between this. So you can, let's say, improve the communication capabilities, maybe more lower latency and much higher bandwidth with the capabilities of the quantum communications. So instead of, let's say, using specific hardware, we could improve the communication links. And also in the core network, we could try to use quantum computers for data centers. So you can have quantum assisted data centers, quantum capable services. And let's say if you have a blockchain network, you could have quantum assisted blockchain. So you could use this kind of technologies for both communication to improve the performance, and also for computing to have, let's say, find more energy efficient resources or resource allocation, or giving you the, let's say, low latency path route optimization. All these kind of problems actually would be transferred into the quantum domain, and you could solve it with quantum computing and circuits in 6G. So actually, there are some simulators that you can use to test some of your ideas. Here, actually, we are showing some of the famous tools. For example, in the demo, we will use Qiskit. This is the quantum circuit simulator. You can do nice notebooks, and you can even use them in IBM Quantum Cloud. There is also Circ, which is similar to Qiskit. So this is also developed by Google. So you can even use them in Google Quantum Cloud. Of course, there are others like PennyLane. Amazon has their own simulator in Azure. So all this kind of, let's say, simulators could help you to build your quantum circuit. So if, for example, in the demo case, we will try to build the circuit for quantum key distribution with Qiskit, and we will try to see some performance analysis, comparisons of different key generation rates and based on the request coming. So you can do various kind of experiments with this kind of simulator/emulators, because you can even put this code into the quantum computers to get your results. So this is actually showing you, let's say, some of the ways you can apply these quantum technologies in the radio access networks. You can have quantum enhanced MIMO networks. You can have improve the channel efficiency with quantum communication, or more enhancements on the reflective surfaces. So these are actually more, let's say, ideas, that things that are happening in the radio access networks. Maybe we could enhance it with the capabilities coming from the quantum communication and quantum computing. to have more better performance systems. So you can also do this. This actually the same idea, just showing you that, for example, all this core network, edge network, transport network equipments, you could try to get, let's say, applications that are relying on this kind of quantum machine learning, quantum algorithm, or quantum computing. They could benefit these capabilities in the edge, in the core, or in the cloud, and you can solve these, let's say, problems related to congestion control, traffic management, spectrum management, or more intelligent optimization problems with the help of these quantum technologies. So one other aspect is actually related to post-quantum cryptography. So this one is actually showing that you could also use post-quantum cryptography with quantum key distribution systems. For example, in the access network, when users try to access to base stations, you could get benefit of the, let's say, key exchange mechanisms of post-quantum cryptography, but maybe in the backhaul to generate these symmetric keys, you can rely on the quantum key distributions systems, for example, in the core network connecting to the data network. So just showing the ways that maybe the hybrid solutions could come when two users are trying to connect to them through the network. This secure communication could be enhanced with quantum key distribution and post-quantum cryptography. So I think this was more or less the introduction. I don't know if there is no question. I can move to the quantum key distribution part. Just wanted to give you a brief overview.
Participants, if you have any queries, you can ask, please. Sir, please proceed, sir.
Okay, sure.
Yeah.
Now I will move to the quantum key distribution. So actually, this is coming from the quantum cryptography. Quantum cryptography is actually leveraging the quantum mechanics to ensure the secure communication. So there are limitations of the classical cryptographic methods, especially when you are when there is quantum computing becomes more powerful, they can break the classical cryptographic methods. So we need to devise new methods with quantum cryptography to protect ourselves against these attacks. Just to understand the things, we need to more delve into the details of what is quantum computing. So in the classical computers, we have these microscopic level bits, 1 or 0s. But this is different in quantum computers. We have these qubits, which is microscopic level. So these are actually some kind of quantum bits. So they can take any form. So it is actually, it can take 0 or 1 before measurement. So this is actually how it is represented, alpha 0 plus beta 1. So here we have this, let's say this is the state of the qubit. So before measurement, we don't know which state is this. So it can be with alpha square probability at 0 state or beta square probability at 1 state. And then here it is showing that quantum bits, actually you can represent them in terms of energy state. So 1 means excited state and 0 means ground state. So there is this energy difference between the physical representation. So you can label them 1, 0, but in physical representations, they are excited state or ground state. So this is how it is represented, these qubits. And what is the difference between the classical information and quantum information? So actually, it's very easy to store the classical information and process it in time and space. But when you move to the quantum information, it's very difficult to store this kind of information. So it is more or less you need to do special treatment for this kind of quantum state, because when you measure it, you are destroying the state. So you need to keep in mind this kind of restrictions. And also, when you want to copy, you can copy your classical bits unlimited times, but in quantum information you cannot copy this. So this comes with this no cloning theorem, and this is giving some restrictions, but we could try to come up with some new solutions to be able to, let's say, send this state from one place to another by special treatment. And then we also have this measurement problem, which is you can measure classical information and it will not be disturbed. But when you have a quantum state, which is alpha 0, beta 1, and then when you measure it, it's going to collapse. So this is something that needs to be taken into account. So after it's collapsed, you cannot go back to the previous state. And this is also needs to be considered. So what is the benefit of this quantum computing, right? So we have this classical computing and the quantum computing. So in an n-bit classical register, we can store n-bit string, but in an n-bit qubit, it can store at any moment a superposition of 2 to the power n bit strings. So this is actually the power of the quantum computing. So you can run in a quantum computer in a single step to compute all the 2 to the power n possibilities at one time. So this gives you enormous parallelism, and which is the reason why quantum computing is envisioned to be so powerful. So you can have this immersive problem-solving capability that gives you this power to be able to find the optimal state in an instant. So there are physical implementations of qubits, which is actually, I will not go too much detail, but you can have this quantum dot qubit, which is spin up, spin down in this physical device. You can have trapped ion qubits, and also superconducting transmon, which is the copper pairs. So these are actually all just to give you an idea that how these qubits are implemented in the physical implementation domain. So there are different variants of this in the physics. So we need to understand actually some of the things that is important in the quantum computing. First of all, there is this superposition. So in a classical bit, you can have zeros and ones, right? But in the qubit, you can have these simultaneous states. You can have 0 and 1 together. So it is alpha 0 and 1. So before measurement, it can be any state. So this is called superposition. And there is another property which is called entanglement. So these are, let's say, if you have these 2 qubits, if they are entangled, 2 particles, if they are entangled together, and if you move this one particle to another place, so they are still entangled to each other. So you can use these capabilities of entanglement to transmit, let's say, some information. So you can use it for communication as domains as well. So this is just showing that these entangled particles, you could use them in your circuit to give you the benefit of this communication and computing power to be so one if you measure one particle, you will immediately know the result of the other particle. So this is more or less the property of the quantum computing. And then the other one is measurement. Of course, if you have a superposition state and if you measure it, it's going to collapse, right? So it's going to be 0 and some ones. So when it is measured, it's collapsing either to 0 or 1, depending on this alpha beta. So there is this interference. You can have constructive or destructive outcomes, right? So you can adjust your let's say wavelengths. So you can make transformations to make a desirable measurement outcome. So this comes actually to do this oracle. So you can have these oracle circuits. For example, if you want to find the optimal state in a huge state space, right? You have a 2 to the power n states, and you want to find the optimal state. You need to design this oracle, which is of course specific to your problem. And then this oracle is going to give you the optimal state. So it will instantly go over each state and it will give you the optimal state to your problem. So this is actually the most, I would say, the difficult part of the quantum circuit, which is the oracle circuit design, because you need to consider the different constraints and the problems are different for each kind of challenges. So you need to make your circuit to be able to solve this kind of optimization problem. And then this, you can represent the, let's say, qubits in a block sphere domain. So you can have the 0 state, 1 state. You can also have other states like plus state, minus state, j state, minus j state. So that means that this phi is the quantum state. It can be alpha 0, beta 1. But you can have transformations, so this mathematical representation. So you can move this state from one place to another with some unitary matrix multiplications, and then you get another state. So if you want to, let's say, if you are in this plus state, you can have some gates to transform this to 0 state, and vice versa. If you have minus state, you can move to 1 state. So this is all just kind of gates, quantum gates that you can transform from one state to another. So compared to classical gates, in the classical gate, we have input bits and we have only one output. So conservation of number of classical bits is not necessary. But in the case of the quantum gate, we have this conservation of number of qubits is necessary. So we have, if you have a 3 qubit input to quantum gate, you need to have a 3 qubit output of the qubits. So you can have phi 1 and output is transformed version of phi 1, which is phi 1, and so on and so forth. So these unitary matrices has some properties which is actually represented here. So you can have input qubit, you multiply it with u, and then you get another state from psi to phi. So you can have these transformations happening. So these unitary matrices actually has this capability, the properties, which is they need to be Hermitian. So they need to have this to ensure the real eigenvalues, and they need to be unitary to conserve the probability after transformation. So these are actually some of the things for if you are building a quantum logic gate, these are some of the properties that needs to be satisfied. For example, there are different gates. So this is the X gate. So this is the matrix representation of X gate. So if for a qubit with one state, and if you pass it through an X gate, you get 0 bit. If you have a 0 qubit, and if you pass it through X gate, you get 1 qubit. So this is actually just inversing operation of the qubit. So So this matrix representation, you can have x0 and you can do the multiplication and you can have one state, because this is 0 state and now you have one state. You can have one state, and if you multiply it with x gate, you can get 0 state. So this is more or less generic representation. If you have a state with AB, A square probability 0, B square probability 1, you can have this transformation and you can, let's say invert the qubits with this X gate. Another one is this Hadamard gate, which is actually this matrix. This is actually randomizing the inputs. If you have a 0 qubit, and if you multiply it with this Hadamard gate, you get this matrix, which means that with 1/2 probability it is 0, 1/2 probability it is 1. So it means that if you have a 0 input, you convert it to another state which is in the middle, half 0, half 1. It's also true for 1, so you can have this different variation of, if you put a 1 qubit to Hadamard gate, you get a different matrix. So this is generic expression. So we will use this Hadamard gate in the quantum key distribution because it's giving you some randomness, right? So you put 0 qubit and then outcome becomes 0 or 1 with half probability. So this is good for secret key generations. So this is how it is used in the quantum key distribution. Of course, there are other gates like Y gate, which is actually moving this from 0 state to J state. So this is the matrix of Y. So you can have 0 state and then it moves to J state. And then you can have Z gate, which is actually transforming from plus state to minus state. So plus state actually is on this equator surface, and you can move this from here to another place with this kind of Z gate transformation. So this is actually showing the, for example, if you have this state, 0 state, 1 state, plus state, minus state, and for example, if you apply Hadamard gate to 0 state, it's going to move to the plus state. Plus state is here. So maybe I hope it's clear from my screen pointer. So it's the plus state. So if you apply Hadamard to 0, it's moving to here. If you apply Hadamard to 1, here it's going to move to the minus state. So it's going to move like this. And then some Hadamard gate has also some properties. If you apply 2 Hadamard gates, the state is not going to change. It's going to keep the same. So if it's the same, if you apply this 1 qubit to Hadamard gate, it's going to stay in the same place. So it's going to move around and come back to the same qubit. There are other gates like rotation gates. So you can have this Rx theta, which is this matrix representation. So you can rotate by theta around the x-axis. You can rotate by theta around the y-axis or around the z-axis. So there are different gates. Actually, you can use them in your circuit. Let's say to solve a problem. For example, these rotation gates, you can use them in the Shor circuit to solve some specific problems, which I will show a brief circuit design of Shor's algorithm to break RSA. So you use these kind of circuits in this kind of gates in this kind of circuits to be able to help you to solve this problem. Of course, there are more complicated ones. So if you want to have this entanglement state, if you want to entangle these qubits. You can have Bell state generator. You need to use Hadamard gate and Z gate. And also other kind of, if you want to use swap, if you want to swap Q1 and Q2, you can use this two qubit swap circuit, or other kind of Toffoli gate or CNOT gate. That could help you to get another kind of logic based on the inputs of the qubits that you put. Okay, so this was just to give you an idea of the qubits. So now I will describe what is quantum key distribution. So quantum key distribution, actually, we have two parties, Alice and Bob, and we want to generate a secret key between them, right? So we want to generate this symmetric encryption key. So you can use this QKD hardware to generate this in the quantum channel. You can generate these secret keys. So how it works? So it relies on this Heisenberg's uncertainty principle and no cloning theorem. So any attempt to measure something in the quantum channel is going to disturb it, right? So this can be detected. And also it's impossible to create an exact copy of the quantum state. So this is some of the benefits of this QKD. So if there is some quantum channel, you cannot break it, you cannot copy it. So it's more or less secure channel. So you need to have this, let's say, fiber channel, which you use for photons to, let's say, if you have an Alice device and Bob's device, you can have quantum signals between them and some regular data channel between them. So these quantum channel is used for quantum keys, and you also use this classical channel for, let's say, making the things agreements between the keys. So you need to have this regular classical channel and the quantum channel to have these keys established. So after these symmetric keys are established between the Alice and Bob, you send it to the upper layer, and then this secure link is established between so these keys are used between the applications, maybe in your video application, other kind of application, they use these secure keys coming from the QKD devices. So you can have this secure communication between Alice and Bob with the help of the QKD. So just to give you an idea, so this is relying on polarization states. So there is this vertical basis. It can either be in this +1 state or -0 state. This is 1 state or 0 state for your photon, or you can generate it with the diagonal basis, which is in this. You can say this is the 1 state, this is the 0 state, which you can use in the quantum channel. For example, if somebody, let's say, uses an incompatible basis, for example, if we are sending this vertical polarized photon, and if is using this cross basis, they cannot be able to get the exact value that is being sent. It can either be this state or this state, which is not correct, because this is what Alice has sent. But since Eve is using a basis that is not compatible with what is sent, it may not be able to get the signal that has been sent. So this is how it is more reliable, secure against these eavesdropping attacks. So a wrong state could appear because Eve can never know which basis Alice has sent. So this is the basic security functions that it proposes. So there are many practical implementations like BB84 continuous variable QKD and others, but I will only concentrate on BB84, which is widely implemented in QKD systems. So BB84 protocol actually is developed by Charles Bennett and Gilles Brassard in 1984. So it is utilizing these polarized photons to encode the bits. So for example, this is actually showing 1 or 0 value depending on your polarization basis. Is vertical or cross. You can have this polarized state or this polarized state to represent your 1 bit value. Or depending on your polarization basis, you can have this polarization base or this polarization base as representing 0, right? So this vertical polarization, 90 degrees polarization bit value is 1. Horizontal 0 degree polarization bit value is 0 if you are using this basis. If you are using this diagonal basis, 45 degree polarization bit value is 0. 35 degree polarization bit value is 1. So this is how photons are transmitted with this after passing through this polarization state. You can have this different polarization bases. You can have different polarization states. So like I said, it relies on this Alice and Bob. They are sending these photon sources, and there is a photon detector in the Bob side. So there is this quantum channel, right? You need to send this photon states, and then you need to also have this classical channel, which I will show why you need this in the next slide. So you need to have these two channels to establish the secret key. And then you use these secret keys in your application domain. So how it works? So this is an example showing how you can generate a secret key with Alice and Bob. So you can have this 0 and 1, and then this horizontal or vertical basis or diagonal basis. So if Alice is using horizontal base, this is how. If Alice is sending 0, this is how it is polarized. If Alice is sending 1, this is how it is polarized. For example, if Alice is sending diagonal bases, then if Alice is sending this 0, it's this state, and this is 1 state. So these are the states, polarization states that are sent in the quantum channel, right? So this is an example. For example, data bits of Alice is 0, 1, 0, 0, 1, 0. So this is what Alice is sending. And then, of course, this is random bits. And then Alice is also assigned the bases, which can be vertical bases or diagonal bases. So Alice is using these bases also randomly, right? So these bits are sent randomly. These assigned bases are selected by Alice randomly. Then, for example, when Alice is sending 0 in a horizontal basis, it can have this vertical polarized state, right? If this 0 is passing through this vertical basis, it is this basis, so it is sending this, Alice is sending this basis. If Alice is sending 1 with this basis, that means this diagonal basis, so it is sending, she's sending this basis. So these are all the polarization states that Alice photons polarization states are sent in the quantum channel, right? And then Bob also has a random basis, so Bob can select horizontal or vertical basis. This is also random because Bob doesn't know which basis Alice has selected. So it's using this random basis. So when this photon is passing through this random basis, it can, if they match, they can pass. For example, here it is matching, it passes. Here also it is matching, it passes. But for example, in this picture, since it doesn't match, it cannot pass, so another state is appearing. So one by one, we can see that there are these red ones that are passing, and the non-red ones that are not passing. So now, after receiving these photons, Bob needs to do another. So after, let's say, measuring the receiving bits, so it can say, okay, I received 0, I received 1, and so on and so forth. But not all of these numbers are going to be selected by Bob, because there are some states, for example, here, that there is no match. So what Bob does is to send this random bases to Alice, and Alice is also sending their own random bases to Bob. So what they are doing is to match the bases. If their bases match, this is done in the classical channel. This is why you need classical channel. If their bases match, they keep the 0 state, 0 bit. If their bases do not match, they ignore this bit, right? So they ignore these non-red places because their bases do not match, but the bases of the matching ones, they get it. So this is how these red ones are selected, because their bases are matched, and then you build your, let's say, secret key based on the matching key. So this is, you select 0, 1 here, you ignore 0, 1 here, you select 1, 0 here, and so on and so forth. So this is the, let's say the more or less close representation of your secret key. This is how it works. Just wanted to give you an idea, because this will be also shown in the demo. I don't know if you have any questions about this presentation.
Participant, please feel free to ask questions. If you have any doubts, you can ask, or if you have any clarity regarding research also, you can get it clarified.
Yes, sir, I have one question.
Yes.
Is there any relationship between the fuzzy logic and the quantum computing logic, wherein even in fuzzy logic also we'll go ahead with the probability representations only? So is there any relationship, or both are very independent?
I am not expert on the fuzzy. Of course, I mean, it's more or less something that is, you would say, not known beforehand, right? So the fuzzy logic, I think, is coming in the classical domain, and you are trying to. I'm not expert, like I said, but you are working on the classical computers, right? But this is coming from the quantum domain, so it's everything is like, before measurement, everything is like in an unknown state.
Correct.
Yeah. So I didn't see any relation that has been established from my side with the logic of the fuzzy logic applied to quantum.
Okay, sir.
But
Okay.
like I said,
Thank
I
you.
am not expert. Yeah, sure.
Yeah. Thank you.
Sir, good evening. Am I audible?
Yes, ma'am.
Sir, this is related to the previous topic, that is related to the security. How does this standardization, that is 3GPP, come into picture when it is giving any security measures related to the quantum?
Sorry, I couldn't understand. If anybody can, I couldn't, because the voice
Sorry,
was
I'm traveling.
far
I
away.
have disturbance. I'm traveling.
Yeah, ma'am, actually,
Sir,
could you
this
please
is
post in the
related.
chat, ma'am? I could convey him.
Ma'am, I can't copy it also because I'm traveling.
Okay, yeah, ma'am, please repeat. I will
Sir,
tell what is it.
So this is related to the standardization. The previous topic, what you spoke, that is how the standardization like 3GPP will come into picture related to the security in 6G.
Okay. So as far as I understand the problem, how does the standardization in 3GPP will come to 6G in terms of security, right? Is what I
Yes, sir, that is
understand. I don't know.
yes, sir.
Okay. Yeah, I mean, in 3GPP, of course, there is this security part that's also ongoing. But this quantum security part actually is something I don't see too much effort in terms of, for example, how we can, in which interface we need to use QKD, or in the previous example we were saying, where should we use PQC or PQKD or any kind of solution in which interfaces. This is actually, I think, still not clear to me as far as I see in the standards. So I think the standards needs to clarify how we can use these technologies, QKD or PQC or any kind of new quantum communication, this kind of new technologies, in which interfaces we should be able to get advantage of this. So these are actually still not clear as far as I see. The things that I described in the beginning, it was just like a suggestion from our side. So you can maybe use in the access network PQC, or in the backhaul network, you can use quantum key distributions to establish the secure key. But still, yeah, I think it needs to be standardized and more discussed, this kind of things in the standardization. So if it is standardized, then the devices will be built according to what is standardized. Then you will see all these technologies, quantum key distribution, for example, in the backhaul network or another network. So I hope it's clear.
Thank you very much.
Participants, do you have any other queries? Sir, please proceed, sir.
Okay, thanks a lot. So I will move to, so I think this was the basic, what I wanted to describe, this quantum key distribution. So you have this public channel to establish this basis and quantum channel. So you get this, so it's more or less, this slide is the same, what I described, just to give you a different perspective. So you have these two channels, and then you have this secret key agreement, and you get the secret. But of course, there are other things that needs to be done, which I will not go to detail, but after getting these keys, this is called sifted keys. You need to have more error coding, amplification, this kind of things to get your secret key. So this is the keys that you get after this quantum key distribution is not the final key, but you need to have more processing to have the secret key established. So this is actually, I will skip this because of due to lack of time. But this is actually showing you the whole process. We only show these sifting keys, but you need to have error rate estimation, error reconciliation, authentication, privacy amplification. All these kind of processes also needs to be done after getting these initial keys, so that you can have the final symmetric key established. So yeah, so HC is actually working on this domain very heavily. So HC has clearly defined these kind of interfaces, what kind of APIs needs to be established with the applications. You can have these QKD modules, and there is kind of like a clear separation of the functionalities where you need to synchronize the keys and other things. So I think more or less HC has this kind of interfaces clearly defined, because QKD is already used in many products and so on. So what you can do with these keys in terms of what can you do in terms of protocol stack, you can get these keys from the underlying quantum channels. You can have a key management system, and this key management system can take these keys from the quantum channel and distribute it to the different protocol stack. So for example, in the IP layer, you can get these keys and you can have IPsec. In the transport layer, you can have TLS, DTLS to get relies on the symmetric key from the quantum channel. And for example, in the MAC layer, you can have MACsec. So all these kind of keys could be reused by these key management systems. Key management system are managing the life cycle of the keys. And you can, let's say, revoke the keys, you can regenerate the keys with the key management systems, and they can be distributed. They can be distributed to each kind of protocol stacks by this system. There is a background noise, I guess.
So please proceed, sir. That is some.
Okay.
Yeah.
So you can also use these kind of links. Let's say if you have a VPN tunnel, you can have these quantum keys established between this Alice and Bob, and then you can have different key management systems in different domains. So this domain 1 can interact with domain 2 with the quantum channel to have a different key, so they can have different wide area networks. So multiple domains they have their own key management systems, and they can interact with each other. And you can have a final, let's say, tunnel connection between Alice and Bob, between applications, relying on this specification. So of course, this application, key management system, communication, these are actually all standardized in ETSI domain. So you can rely on these protocol stacks to establish your connection with QKD. And in terms of the radio ORAN networks, you can have these radio units, distributed units, and central units. All these units can be interconnected. The encryption messages, the keys of encryption could be taken from the QKD links between the distributed unit and the radio unit. Of course, these needs to be upgraded to quantum devices. So all these keys between this, let's say, central unit or cloud core network, you can establish these keys with the quantum key distribution, and you can put them to IPsec or MACsec layer to have your secure connection between the devices. So this is more or less showing a vision for quantum cryptography usage of QKD. Of course, there is also PQC, this domain. So, yeah, I think due to lack of time, I will move to the demo, but just to give you this thing that quantum key distribution, there are trade-off of secure key generation because longer distances reduces the key rates. There's channel noise. So this is used in optical fiber. You can go up to hundreds of kilometers. You can also use it in satellite communication, right? You can use satellite for key distribution between the terrestrial networks. So you can establish these secure keys over the satellite. But yeah, so the thing about this quantum key distribution is that it is providing you an everlasting security. So even the key exchange algorithms are broken, the keys are going to remain secure. So this is providing this everlasting security that is immune to future cryptographic analytics advances. So, for example, PQC algorithms, maybe there is a chance that they can be broken in the future, but QKD gives you this benefit that these keys, since they are generating on the fly, it gives you this security guarantees as long as your authentication channel is not broken. Because you need to. Sorry. Okay. Yeah, so I will move to the demo just in the last 10 minutes, just to give you an idea of how it is done. So I will show you a demo about, I hope you can see it. The screen. So what I will do is to show you this quantum key distribution system in a Qiskit library. So I have this installing this Qiskit library and key class kit to visualize the circuit. This is downloading the libraries. So what I will do while it's installing these things, I will try to show you the theoretical part. Okay, so this is what I will try to do. So I will try to generate a BB84 circuit, visualize the circuit, and simulate the circuit and get some measurement results. So what I will do is to define a function, BB84 circuit function. So this is getting 2 qubits input and 4 qubits input and 4 bits output. And I will select a basis function for Alice, which is random. For example, 0 for standard, 1 for Hadamard state. So this is the example basis for Alice, and this is the example basis for Bob. So what is this is was doing is if the basis if you go over the basis of Alice, and if there is 1, I will apply Hadamard gate. If it is 0, I will not do anything. Then I will, let's say, assume a transmission. And in the Bob side, it will go over its own basis. If the Bob's basis is 1, it's going to apply Hadamard. If it is 0, it will not do anything. And then I am going to measure the state, measure the qubit, and return the circuit. And then I will try to visualize the BB84 circuit. So here, this is visualizing Alice and Bob. So Alice is applying Hadamard gate to Q2 and Q3 qubit. Bob is applying in receiver side Hadamard gate to Q1, and then also Hadamard gate to Q3, and then they measure the qubit, and this is the classical bit that you get. So you have 4 qubits input and 4 classical bit output, which is the potential secret key. And then we will run this for 1000 times, and we will get the results, because each time we run, we will have, after passing this to Hadamard, because we will have 0.5 probability 1 or 0.4 probability with 0. So you will have different outcomes if the gates don't match. So we will try to generate the histogram of the measurement. So here, for example, in this run, we have 273 times we get 0 state, 0 bits, and then we will get this as our key, secret key. Okay, so this is what we are going to do. This is just showing the results of the secret key. So after this installation, I will import these libraries, Qiskit library, visualization library. Then I will run this BB84 circuit. So you have this Alice basis, it takes n qubit input, n bit output. So if the Alice basis is 1, you get apply Hadamard. So you transmit it, and if the Bob basis is 1, you apply Hadamard, and then you measure. So this is how it is done. And then here I select random bases, for example, 00010 for this, 10010 for Bob. So these are random bases. I put it into the quantum circuit, and then I draw it here. So this is how it looks. So for example, here, Alice didn't apply Hadamard, but Bob applied Hadamard. Here, nobody applies. In the second qubit, nobody applied Hadamard, so it's direct measurement. In the third qubit, nobody applied Hadamard, so it's direct measurement. In the fourth qubit, both of them applied Hadamard, so it is here. Alice applied Hadamard, Bob applied Hadamard. In the last qubit, nobody applied Hadamard, and it's here. There is no. So you can even change the things, and then, for example, I can also apply Hadamard in Q1, and you can see that in Q0 you have Hadamard from the Alice. And then after this, we run the circuit 1,000 times simulator, and then we try to get the qubits histogram. So here, since we have the same match, there is a perfect match between the bases, we will get exactly 1,000 times 000. For example, if there is no match, we will get different result because the bases don't match. So you will have 513 times 001 and 511 times 000. And then what we do is to select the keys that gets the largest. So here we measure the outcome of the counts, we get the most likely outcome, and then we measure the bits. And then we get the secret key. So this is how we get the secret key. If we run this like this, so we have most likely outcome is 0001 because of this histogram. And then, because this is appearing 513 times. And then we get the matching bases. We check the matching bases. For example, this is the measured bits, which is 0, which is coming from here. You read it backwards, 100. And then you check the matching bases. For example, here, first, second, and all of them are actually matching here. And then you get the first qubit doesn't match, but the second, third, and fourth are matching. So you get these bits as your secret key because they are the ones that are matching. This first one is not matching because you use different bases here because we used 0 and 1, but the other are matching. So we get the measurement result of the last 4. And these are all. This is now our secret key from the simulation. Yeah, I think this was it. I wanted to show in this brief time. I don't know if you have any question on this simulation.
Participants, do you have any questions? Sir, please proceed, sir.
Okay, sure. Yeah, just to conclude, you can do more analysis, right? You can increase the number of requests, and you can measure the key generation rates and other kind of metrics that you want to do with this kind of circuits. So this more or less gives you an idea that this was a simple QKD, but there are more complex circuits that you can use, which I didn't have time to go. For example, Shor's circuit you can use to break RSA. with a very simple examples. But you can use this kind of circuits to help you with your analysis. Yeah, I think this was all. So I just wanted to give you an idea of QKD and maybe some kind of how it can be applied to 6G networks. So they are still ongoing. Standardization efforts are ongoing. So I hope this was helpful just to give you an idea how it works and can generate some new ideas in the future. Thanks a lot.
Sir?
Yes.
Yeah, sir,
I think
thank you.
I am done with the presentation.
Yes, sir. Yeah, thank you so much for the clear presentation, and it is like gave insights into how quantum will be with the 6G and 5G networks as well. Along with that, the demo session is also good. It would be helpful if you could share the PPT as well as the Python file so that it will be helpful for the participants to look forward to it.
Okay, sure.
Yeah, really thank you so much for accepting a last minute invite and participating in this and giving us the better insights into your domain, sir. I request you to stay in the session, sir, because we're going to start the or validatory function now. I request you to please stay online, sir.
Okay, thanks a lot.
Yeah,
thank
thank you so much, sir. Yeah. Audience, participants, do you have any queries or if you want to tell something or ask something to him, please feel free to ask. It is open to you now. Do anyone want to speak?
Hello.
Yeah, ma'am, please proceed.
Sir, we are using here ATAL and we do classical distance only. Yeah, we need to be
Ma'am, your voice is not clear, ma'am. Ma'am?